Well, welcome to another Fibre Laser Learning Lab. We're going to continue our pursuit of colours today, and I say colours because I really probably mean colour. I mean, we've got a lot to learn because, as we can see from this colour here, depending on how I move that in the light, I get a completely different colour. And I think last time we established why that might be happening, and that's because of the surface texture and the way in which the light is reflecting off that surface texture. Now that's, I suppose, what we would naturally call an iridescent colour, right? But when we look at some of these other colours here, okay, there's a slight change as we move around in the light, but they're relatively stable. You know, these sort of lovely little sort of a pale jade green and pale blue, and then we move to the mauves, the lilacs, and then the pinks, then these crimson colours, and finally here we've got gold, which is a pretty stable colour. I mean, even if we catch those in the light right, you can see that they've got iridescent features as well, right? But gold is one of those colours which is produced, I believe, by low temperature heating of the surface to manipulate the surface texture. Here we've got our old favourite oxide marks, and as you can see, the outer or lower temperature range of colours is the yellow colour, and the blue is the much higher temperature range in the middle. Okay, so I'm claiming that the gold is all to do with low temperature because this is where we're finding it, on the low temperature region, around about 170 to 200 degrees C, something like that. So a quick recap of what we discovered last time. We found that this heating to cooling ratio here is very important. We could get 5,000 pulses per millimetre if we ran at 100 millimetres a second, but we were getting only 250 pulses per millimetre if we were running at 2,000 millimetres a second. So the amount of heat that we were putting into the product was directly proportional to the speed. The overlap between the dots was one of the control features that we realised we could play with last time, because this heating and cooling effect meant the less distance you travelled between each pulse, the more heating you could put into a single spot and the hotter you could make that spot. Now the second feature that we found was that if we could overlap these lines, we could increase that heating effect as well. Although we'd previously talked about all sorts of other ways of controlling power on this machine, using higher or lower frequency above and below the optimum peak power frequency, although focus is there as a feature for us to play with, it's not the most reliable and accurate form of control. There are three features that will allow us to play with the heating effect on a particular spot. One of them is speed, as we've just mentioned here. One of them is line spacing. Let's call it pitch. And the third one is percent power. Now these are all predictable and easily controllable features. So from what I learnt last time, I hope I've got sufficient mastery of these parameters that I might be able to go hunting for gold. Just one colour. Let's not get too ambitious. We need to walk before we can run. So during today's session, I hope that I should be able to prove to myself what I believed all the way along, that there is no single formula for gold. Gold will depend on different mixes of these parameters. There will be all sorts of parameter mixes that will give me gold. Now some will be dark gold, some will be light gold. If I start raising the temperature of the surface too much, I'm very confident I should be getting into this red zone here, which is the next temperature zone up from gold. And therefore if I mix red with gold, I should probably finish up with a coppery colour. So when I've got to a coppery colour, I know that I've pushed the boundary too far. And what we saw last time was that the colour that's actually on the surface of the material is not necessarily the colour that we perceive with our eyes. It is a mix of all those colours that are on the surface. So there is a very complex relationship between these features here, what happens on the surface of the material, and what we perceive with our eye. Now, whether that is actually controllable and predictable is what we're going to try and find out with our hunt for colours over the next few sessions. My starting point is gold because that's probably the easiest of the colours to work with. We will then start probably increasing things like the pulse width to see if we can find more colours as we increase the temperature. Right, well, we're going to start off with our 4 nanosecond pulse at 500 kilohertz. I'm going to go for 50% power to start with, and a speed which at 1500 is sort of okay. That should give us a reasonable gold from previous experience. Okay, now forget about the black clump there. I'm reusing an old plate here. So there's our initial gold. I've got another little lump there which I shall steer around as well. But after that everything gets clear. If I increase the speed, I should be reducing the number of pulses per millimetre, which will make it run cooler. It might drop off the bottom of the scale, or it might make a slightly paler gold. Let's try 2000 and leave everything else the same. But it's still a very pale greeny gold, so that prediction was correct. So we've gone a bit cool now. So how do we increase the power? We'll leave the speed the same at 2000, and this time we want to increase the power. So we can increase the power by probably lowering the pitch a bit. So from say 10 microns, let's go down to 8 microns. So for number 3, we're going to do 8 microns. That was 10 microns, just for clarity. We've gone back to a slightly darker gold. It's not quite as green as that one. So we'll go another couple of microns and make it a little bit hotter. You can see we've gone too much because we've got a hint of red in there now. See, it's a slightly mauvey colour. So we've actually put too much heat into the gold now, and we've driven it back towards red. So when we look at that under the microscope, we'll probably find we've got quite a lot of red sitting under there. We will go and check these under the microscope. So let's go back and we'll try 7 microns. And yes, we've got our gold back again. It's a slightly darker gold. It's not copper coloured. It's actually quite a nice coloured gold, and it's not dissimilar to the one that we had at the top here. Let's move on from this one and see what we can change here to still keep gold. So if I drop back down to 1500, which we haven't had before, with 7 microns, what will that do for us? We're putting more heat into the job, therefore it probably might send us towards the red again. We might get a copper colour, who knows? Wow, so 1500 with a 7 micron pitch is just putting too much heat into it because it's turning it blue. What else have we got? We can play with the power, so we'll reduce the power to 30%, and sure enough we've got a bit of a gold back again. It's a pale gold, maybe 20%. Let's try 20%. Well, we've got so little power on there now that we can't even see it, so it is a very, very, very pale gold in this light, but it's almost invisible. So we need to put the power back up. We could decrease the pitch to get the power back up, so we take that down to 6 or 5 microns. Let's go down to 5 microns. It's darker, but we've overdone the power decrease, I think. So we've either got to decrease the speed to get the power back up. Why don't we try that? Instead of 1500, let's go down to 1000. That was 20%. Hasn't really given us a great deal of advantage. We haven't got our gold back. It's goldish, but it's extremely faint in the background. So let's gradually creep up on the power again. So we go up to 30%, see if we can get our gold back. we're almost into a blue here, the same as we were here. So the biggest difference between most of these colours is this pitch. I've closed the pitch up. So let's change from 30% power, 5 microns. Let's go back up to 7 microns. I haven't done that before, have I? 37? No, I've done a 57, but not a 37. And we're down at 1,000 millimeters a second now, whereas we were 2,000 here when we were doing 7 before. And yes, we're beginning to get our gold back. More spacing. Let's try 8 microns. Yep, we've still got our gold. It's not bad, it's a little bit lighter. Let's try 9 microns. 9 microns still works. They're all pretty similar. We'll go back to 10 microns. Well, it's still gold. I think you'll see they're all much of a muchness, those golds there. It's getting a little bit paler, but then again, look at the difference. 10 microns at 1,000 millimeters a second, and 10 microns at 1,500, or even 10 microns at 2,000. Look. So here's 10 microns at 2,000, slightly blue, and then we've got 10 microns at 1,000. So that's a huge range in which we've got a sort of a goldy colour. I mean, to be honest, that 10 microns at 2,000 is one of the brighter golds. It is a nice bright gold. These have got a slightly duller hue to them. That one is definitely a nice, although in this light it looks slightly green. When you catch it in the light that I'm seeing it most of the time, that looks like the brightest gold of the lot. So if I put the power up, we're probably going to force it towards a darker colour again. But let's try that, shall we? Let's go 10, 1,000, which is hot, 10, which is cool, because we've opened the spacing up, and now we'll put some power into it as well. So let's go from 30% to 40%. It's got a slightly blue cast to it. We won't know until we look at it under the microscope what the colours are within that gold surface. So we'll push it up a little bit more. We'll go up to 50%. And then we shall have a comparison between 50% at 1,000 and 50% at 1,500 and 2,000. And yet, now we've done it, we've pushed it over and we've gone to blue. So we've gone too hot now. 50% at 1,000, it's too hot. We could leave it at 50% and we could increase the pitch again to say 12 microns. That should cool it down. So now we're cooling it down. It's no longer a bright blue. We're getting back towards more like one of these colours here. So we could probably go a little bit wider on the spacing, say 14 microns. So now we're bringing our gold back into play again by cooling it down, opening up the spacing. Can I open up the spacing a bit more? 16 microns? The answer is yes, I can, and it's becoming an even better gold. So we've gone from a blue to a slightly blue hue. That gold there looks almost as good as number 3 or number 1. A convenient point to stop maybe and take a look at these first set of results. Now, okay, we've got all these other little golds in between, slightly different colours, but the two that seem to match are these A3 and B10. Now this may actually be more significant than I thought when I first picked it up in the previous session and dismissed it. So B10 is done at 1,000 millimeters a second with 50% power and 16 micron pitch. A3 is 2,000 millimeters a second with 50% power but this time with an 8 micron pitch. Let me just remind you of that little picture which I talked about in the previous session. If we look at A3, we've got 125 lines in a millimetre and we've got 250 pulses in a millimetre. That's a total number of pulses of 31,250. And if we check the same thing for B10, we find that we've got 62.5 lines per millimetre with 500 pulses per millimetre, which again comes out to the same number of pulses per square millimetre. So this might be worth investigating just a little bit further to see if this is just a coincident set of data, because it could well be that there is a relationship between the lines per millimetre and the pulses per millimetre. So taking that to a conclusion, I wonder what happens if we decide to put in 32 microns. That's really pushing it, because the beam is supposed to be 60 to 65 microns. That means we've basically got around about 3.5 lines overlapping here. Maybe we'll go to 20 and we'll see what happens at 20 microns. That'll give us 3 lines of overlap. It means we're going to get 50 lines per millimetre, and 50 lines per millimetre divided into 31250 gives us 625 pulses per millimetre. And then when I take a look at my chart here, 625 pulses per millimetre as a speed of 800 millimetres a second. So that defines for us 800 millimetres a second with a 20 micron spacing. Let's test that, should we? Well, I would actually say that that and that and that, you can't see it in this light, but they certainly all look the same. What else can we predict? I think if I stretch this much further, I should be in trouble. We could try 25. That gives us a running speed of about 650 millimetres a second. Still leaving everything else the same. Well, that's still a perfect match. We might be onto something here. 10 microns. Well, that looks like another success. Big difference in the settings, no difference in the colour. Well, the maximum speed we can go to is 2000. So let's leave 2000 50% and work out what the micron spacing should be. Well, it's going to be 8 because we've done it already. We did it for number 3. So we've gone from 850 to 2000, 20 microns to 8 microns. We will do it again just so that we've got it in comparison. And there it is again, 4 in a row, all exactly the same. 800, 650, 1600, 2000, 20 microns, 25 microns, 10 and 8. Phenomenal change of parameters, but all arriving at the same result. So we're going to repeat these 4 results here, but with 100% power rather than 50% power. Normally, when you throw 100% power at something, you get the sparkly, crinkly surface, especially with these small pulses where you tend to dig in quite a lot. I'm not sure that we're going to get too much colour change. I am moderately confident that these are all going to be sparkly gold. Sparkly, yes. Just a lighter shade, yes. Still a gold, I would say. Erring towards the silver, but definitely got a gold hue in there. When we look at that carefully, we may well find that there's some blue in there, but we'll carry on and we'll see how the others match up to that particular pattern. It's still a light gold, very light now. It's a similar colour to the one beside it, but when you turn them to the light, they've got different reflective characteristics. Let's go for the last one, which is 2008 microns. Well, that's another success. Now I'm going to jump off a cliff. I've got no idea what colour I'm going to get, but let's try exactly the same test. Let's double the pulse density. So here's my next test. We're going to use exactly the same speeds with 100% power, the same, which gave us golds. Everything here remains the same. The only thing is we're going to halve the pitch between the lines for each one of these. Now whatever colour that one comes out, I would expect that, that and that to match. That's if we're onto something interesting here. Now on the basis of our A3 test, which is what we did at some stage, it's hinting towards maybe somewhere down here in the bluey emerald green region. Pale blue, pale green. We'll have to wait and see. Silver with a hint of silver with a hint of bluey green in it. Let's try the 650 one. Well, all I can say is there's another matching one, silver-ish, with a hint of possible hint of green in it. Now we've got a pale blue, a sparkly pale blue. Well, that's a perfect match. It's a very nice pale blue. Now, just as I've gone to change those settings, I've realised I made a slight mistake last time, and this one should have been 5 microns, and that is 5 microns. So there's a very slight colour difference in the blue when I went to 5 microns as opposed to 4 microns. So 4 and 5 microns beside each other there. Yeah, they're very nice golds. Perhaps I ought to sit down and work out what the pixel density is in these and see if we can replicate these, because these are very nice golds. The others are fairly weak in comparison. I mean, you can see, look, when I even as I move those around in the light, they really don't change a great deal. All the others have gone dark, but those are actually showing their true colours. And that's because they've got a disrupted surface finish. They're reflecting all over the place. Particularly these last two here, which are the 1600 and 2000 at 2 and 2.5 microns. So I've chosen a range of pitches here from 2.5 up to 12 microns, and I've calculated the appropriate speed which will generate 100,000 pulses per square millimetre. So the 3, 4 and 5 micron tests come out more or less the same as the standard 2.5 that we started off with, which is that one. So we've done the same test again, but we'll use the copper this time and see whether or not the copper gold in this last row replicates reasonably well as well, or whether it can extend down further than this. As I said, these are all gold, but some of them are fairly weak and pathetic, and they've got a shiny surface on them, which means that they can only be viewed in one direction. So we're definitely after these speckled colours, because these are the colours that are going to, if you like, survive in almost any light. So we've now chosen the coppery gold and matched up the speeds so that they come out to 156,500 pulses per square millimetre. And we'll run 10 more results off and see what we get. Now these first three at 1.6, 2 and 3 microns are all very, very good. They're all that lovely coppery gold colour. Now these others are also pretty good coppery gold. You can see they run all the way down as a gold, and in fact they are a slightly coppery gold, more coppery gold than the ones beside it. So we can clearly see on here those that enjoy playing with the light and those that are not very happy with it. But I think the case is now proved that there is a whole range of speeds and pictures which, provided you set the other parameters correct, you can vary quite a lot if you stick to a certain rule, and the rule is pulse density per square millimetre. Now, although we found all sorts of golds on there, and I've been very successful with my gold mining today, we can see the ones that are obviously standing out. These are the speckled ones. So they're slightly deeper, and they tend to be the finer pitch ones that you can see in this light, which is great because it means they're no longer particularly sensitive to light direction. They pick up the light from all directions, and that really is what my total aim will be, to try and produce a palette of colours that are virtually impervious to the direction of the light. We're just going to have a look through 2 or 3 of these samples under the microscope, just to show you the textures that are created by the different parameters. All these samples that I'm going to show you are done with 100% power. This first one is 6 microns pitch, 650 millimeters a second. I think you could probably guess from that fawny look that it may well be a gold. You can only see that it's gold in one direction. In another direction, when you turn the light across it, it's black. You wouldn't know that from looking at that, because that looks as though it's a pretty good gold. Let's take a look at it in high magnification. Well, I can tell you that that surface there is basically hardly disturbing the surface of the material. We've got all these marks here, which are the like the oxidization marks that you've seen on my flat metal sample. We're not actually burrowing into or disturbing the surface of the material very much. Maybe just in 1 or 2 places where the power is high in the centre of the beam, we might just be breaking through the oxide film. So it's not a uniform film that we're seeing. It's an effect, a colour effect from a continuously variable film. Now, this was done at 3 times the speed, almost 1600. But this is done with a 2 micron step. There's definitely some yellowy cream in there. That is virtually the same colour as the one next to it, except that this one is glittery. Let's see what's caused the glitter when we look at the high magnification. What we've got there are blobs and pits. The green pieces, which I'm bringing into focus now, and look particularly at something like this one up here, which has got a lot of depth, because you can see that from the way I'm bringing the colours in, those colour bands. Can you see all those colour bands just round there? I mean, they are variable degrees of oxide thickness within a pit. And then if I change the focus and bring it up to the surface, look at all these lovely heat patterns, these colours that we've seen on my oxide film. Look, the blues, the browns, the yellows, which are in the background. I mean, it's a right mixture of colour here at the surface. Does it look as though it's going to come out gold? Well, there's a predominance of yellowy stuff there, I suppose. That's definitely surface disruption, and that has caused a sparkly colour. Now here's another sparkly one. More or less the same colour. I would say that on the surface of it, this looks as though it might be a lighter colour. And this was 2.5 micron interval with a 2000 millimetre per second speed. Not a huge difference from the previous one. So we haven't got very much yellow in this one. We've got our large changes in depth. We've got probably 3 or 4 microns there, I suspect, if I was to measure it. We've got this sort of pale yellow, which looks as though it's on the surface. And then we've got these pits here, which look as though they're buried into the surface. And we've got a few bits of this orange and red that we saw on the previous one. But at this high magnification, the colours are nothing like the previous one. And yet, stand them side by side and they look virtually the same to the naked eye. This, again, to the naked eye, it's not quite a sparkly gold and it's not a flat gold. But then again, the parameters for this are totally different than those that we've just seen. Now, I'm going to move it up. You can see the line across the top there, which is the line that created this pattern. But this, unlike the others, is done slow at 800 millimeters a second with a huge pitch of 20 microns and 100% power, the same as the others. Now you'd ask yourself the question, why isn't that a blue? Because there's a greater predominance of blue in that pattern than there is gold. Nope, it comes out to the naked eye as a slightly non-flat gold. It's not polished gold. Again, it does lose its colour when you turn it away in certain types of light. Well, I could spend hours looking at this stuff because it's absolutely fascinating. Well, it's very difficult to catch my test plate in the right light to show you all the possibilities that are happening. I mean, these are all, most of these are golds. As it happens, these came out quite well. You can see that they're all gold. Up here, they look white, but in fact, these are nice sparkly golds. But what you can see on these pictures is that these are sparkly, and the ones that we've just looked at on the screen in high magnification, this one here, which is a flat gold, this one here, which is a sparkly gold, and this one here, which is a semi-sparkly gold. So you've got this fairly crude image as a reference starting point. And then what I've done, I've taken images of each one of my tests. This one is A1 at 50 times magnification. This one's A1 at 400 times magnification. So you've got low and high resolution for each one of those test squares. Okay, you've actually got the test square picture here. And beside that, what we've got is a record in the form of a spreadsheet with all the parameters and two quick thumbnails of 50 times and 400 times between each result. So if you really are interested in seeing these images in high resolution, then I'm happy to send them to you. What you need to do is to add your email address, a disguised email address. Write it out in words, john.smith@yahoo.com, all as one great big long string. I will send you a link to my Dropbox where you'll be able to download all these onto your own PC and study them if you wish to. Now these pictures, good as they still are only probably about 80% of the quality that I can see directly into the microscope. The microscope gives a much clearer image of what's going on. But these are very good representations and will give you a feel. There is no depth. All I can do is find an optimum focus when I take the picture. So I think we'll conclude at that point, and next time we might go searching for some different colours. Now we've got a little bit of an understanding of how it all works. Thank you very much for your time, and I'll catch you in the next session.